How can we show that a set of connectives is functionally complete? Let's consider. Hello, I'm Chico. Welcome to the Philosopher Channel Introduction to Propositional Logic course. In previous videos, we saw what the different possible connectives are and how to define one connective using others. In this video, we'll show how to use just some connectives to define all the possible connectives, and that will be what we call being functionally complete. And the first set that we're going to talk about is or, and not. So those three connectives together, that is a functionally complete set. Well, first let's see how they can define the zero-place connectives. And there are two zero-place connectives, the verum and the falsum. The verum is always true and the falsum is always false. And you can see that my true tables for the verum and the falsum look a little bit different. There's an extra box at the bottom of each one. And that's just to match it up with the true tables that we're going to have to use for the ors and the nots, because those are going to have to be multiple place connectives. We're going to have propositions that are attached to them, and those propositions are going to have to be true or false. But notice there's still the same true tables. The verum is always true, the falsum is always false. So how to define the verum using just ors, ands, and nots? Well, the most obvious thing is that we need some kind of tautology, something that is always true. And the easiest one we have is A or not A. So let me go ahead and go through that. The not will flip the T's and F's. And the disjunction is true when at least one disjunct is true. And that happens on both rows. In both rows, we have at least one disjunct being true. So using or and not, we've come up with a formula that's identical to the verum. And now for the falsum, the thing that's always false, the most obvious thing would be that we need a contradiction. And the easiest contradiction is A and not A. The not will flip the T's and F's. And the conjunction, only true when both conjuncts are true, which doesn't happen in either row in this case, so both rows are false. And there we have it, a true table that is identical to the falsum. Now, when it comes to one-place connectives, we only have 4 that we need to cover. And actually, since we're considering not as part of our set, we don't have to worry about that one. That one is good. But for the other 3, connective 1 takes whatever alpha is and turns it into a true. And that is identical to what we just saw for the verum. All we need is a tautology, and the easiest one is alpha or not alpha. And that is what we have on the top there. And then for connective 4, that just turns everything false. And again, all we need is a contradiction, and that is alpha and not alpha. And that's the second thing we have there. And then the only other connective we need to worry about is connective 2. And that takes, if alpha is true, then connective 2 and alpha is true. And if alpha is false, connective 2 with alpha is false. So really, the true table would just be alpha at that point, right? It would just be the exact same thing. So the formula that's identical to connective 2 is just alpha by itself. And that's it. Now on to two-place connectives. And there are 16 of these. Of course, we're using or and, so those are 2 that we don't need to worry about, but that's 14 more that we need to worry about. So that's pretty hefty. We're not going to go through every single one of them, but I'm going to show you the strategy on how to figure it out. The first one is a little unique though. That's the one where in connective 16 where everything is false. Well, again, just like for the falsum, we use a contradiction, alpha and not alpha. The not flips the T's and F's. And the conjunction is only true when both conjuncts are true, which doesn't happen on any of the rows. And there it is, identical to the connective 16. But for the rest of these, there is at least one true in there. So here's the strategy that we're going to do. Look at, and we're going to use connective 6. And not for any specific reason. Connective 6 is just one chosen randomly by Smith in the textbook, totally arbitrarily, right? We're going to pick 6, and that's going to show us the process on how we can do the rest of them. So what we'll do is for each line, that we have a true. So notice connective 6 is true here and here. For each of those lines, we'll put a conjunction based on the truth values of alpha and beta. If alpha is true, then we'll write alpha. If beta is true, we'll write beta. If alpha is false, we'll write not alpha. And if beta is false, we'll write not beta. On the first row, alpha and beta are true, so we have alpha and beta. On the third row, alpha is false and beta is true, so we wrote not alpha and beta. And once we've got a conjunction for each one of those, remember that a conjunction is only true when both conjuncts are true. And that only happens on that one row, right? Not alpha and beta, that only happens on row 3. On any of the other rows, you don't have a not alpha or you don't have a beta, right? Alpha is not false or beta is not true. Something like that happens on one of the other rows. So on all the other rows, these conjunctions are false. What we'll do then is we'll take these conjunctions and we'll put them together in a disjunction. And what that does is this disjunction is true when at least one of those disjuncts are true, right? And those disjuncts, remember, are only true on the rows in which we've got them. So that means if you're on any of the rows where those disjuncts are not, then this disjunction is going to be false, which is what you want, right? So that's how we come up with our formula. Now let's just make sure that that's the case using a truth table for that formula. First, we'll take care of the not with the not alpha, flips the T's and F's. Then we'll take care of the two conjunctions, and those conjunctions are true only when both conjuncts are true. That looks like it happens here and here. The rest of them are false. And finally, that disjunction is only false when both disjuncts are false, and that happens in this row and this row. Other rows are true. And sure enough, we have two identical truth tables. So sweet. We have used ors and ands and nots and have come up with the exact same truth table as we would have with connective 6. That means we've defined connective 6 using ors and ands and nots. So that is the method for defining two-place connectives using just or, and not. We can actually use the same exact method for three-place connectives and above. So notice here I have a three-place connective chosen at random again, and it's just FT, FFF, TTF. And on the right-hand side, I've written conjunctions using the truth values of alpha, beta, and gamma. So for example, on row 2, where alpha is true, beta is true, and gamma is false, I have alpha and beta and not gamma. On row 6, where it's alpha is false, beta is true, and gamma is false, I have not alpha, yes beta, and not gamma. And for row 7, false, false, true, not alpha, not beta, yes gamma. So all you would have to do is to put this together in a disjunction, and there you would have a definition of this three-place connective using just or, and not. So we've defined the zero-place connectives. We've defined the one-place connectives. We've shown how to define the two-place connectives and above. Or, and not have got to be functionally complete. They can be used to define all possible connectives. Interestingly, and not can be used to define or and not can be used to define and. And these are because of what, remember, are De Morgan's laws. If you don't remember, you can watch that video again. The De Morgan's laws are specifically laws that show that these two are what are called duals. And in the textbook, it says that two n-place connectives, star and dagger, are duals if star alpha 1 through alpha n is equivalent to not dagger, not alpha 1 to not alpha n, and dagger alpha 1 to alpha n is equivalent to not star, not alpha 1 to not alpha n. Which sounds heavy, I know, But basically exactly the situation we have right here, right? A and B, alpha and beta, is equivalent to not alpha or not beta. And then alpha or beta is equivalent to not alpha and not beta. So I'll go ahead and do these truth tables for you, and I'll do them both at the same time. The nots will flip the T's and F's. The disjunction, true when either disjunct is true, otherwise false. And the negation flips all those. The conjunction, only true when both conjuncts are true, otherwise false. And the negation flips that. And there you go. So you have and being defined by not and or being defined by not and. So that means that not and or are functionally complete by themselves, and not and are also functionally complete by themselves. Now, this information will be important because what it means is that if we can take other connectives and define not and or not and using those other connectives, then we'll have proved that those connectives are also functionally complete, because then they'll be able to do everything that not and does, which is everything, right? Interestingly, there is a connective 9, that by itself can define not, or, and. That means that this connective by itself is functionally complete, right? It is in the singleton set of a functionally complete set. And that's pretty wild. And you can see the truth table for it down here. That symbol that I have put in there is called the Sheffer stroke, and the truth table is FTTT. So let's use that truth table to define first not alpha. Now the truth table for not alpha is going to look a little bit different, because here we're talking about a two-place connective and comparing that with the not alpha, but it's going to be the same thing, where alpha will have all the T's and F's flipped by that not. So that's what the truth table looks like for a negation when you're dealing with an alpha and a beta as well. Now let's look at the formula using the Sheffer stroke that is identical to not alpha, and it's alpha Sheffer stroke alpha. You can see in rows 1 and 2 that we have a true situation, and that is row 1 on the truth table. So that's going to make this false. And then we have false on the second 2 rows, and that will be like the last row here. So that will be true. And there we go. We have a truth table identical to the not alpha truth table. Now let's check alpha and beta, and the equivalent formula is alpha stroke beta stroke alpha stroke beta. And these alpha stroke betas are exactly identical to the actual truth table for alpha stroke beta, right? We have the exact same format. So I can just copy straight down the middle, FTT and FTT. T. Now for the stroke in the middle, we have on the first row FF, and that is this guy right here. So we have a T. And then on the rest of the rows, we have TTs, and that is this row right here. So those are Fs. And there we have an identical truth table to the and. Now let's try the or. For this one, the formula is alpha stroke beta stroke beta. So now we have a bunch of rows where we have a TT, and that's where we get an F. So I'll put Fs in there. And then a bunch of rows where we have FFs. So that's where we have a T. I'll put T's in there. Okay, now we're going to have to look row by row. On the first row, we have F and F, that is this guy right here. So it's true. On the second row, we have FT, which is this right here. So we get a true. In the third row, we have a TF, which is this right here. So we get a true. And then finally, in the last row, we have a TT, which is this guy right here. And we have the identical truth table for a disjunction. So the Sheffer stroke all by itself is functionally complete. Interestingly enough, or and by themselves are not functionally complete. Now, how can we tell that they're not functionally complete? You're actually going to have to do a little bit of reasoning to tell when a set of connectives are not functionally complete. So let's look at what happens on row 1, where alpha and beta are both true. On that row, or is true and is true. Now, on that row, not alpha is actually false. So how do we combine the ands and the ors to get ourselves a false on that row, to make something identical to the not alpha, in other words? Could we do alpha and alpha? No, alpha and alpha would be true on that line. Could we do alpha or alpha? No, alpha or alpha would also be true on that line. Could we do alpha or alpha and alpha? No, that would also be true. In other words, because they're all true on that line, there's no way for us to be able to define a negation on row 1. So and or are not functionally complete. We can't use them to define all the truth functional connectives. So not functionally complete. That's it for this section. I will say that the exercises that are coming up, 6.6.3, which is, are due next time, are very difficult. So feel free to check the video while you're doing the exercises, just to give yourself some clues, or really just to help yourself out, because they're very difficult problems. And yeah, I don't want you guys to get frustrated. So yeah, check out the video on that, and I'll see you in that video. Adios.